And here are some naive weight mapping strategy. So for example, here what you can do if you want to map those kernels into the memory. So what you can do is to unroll each kernel, let's say 3 by 3 by 128. So 3 by 3 by 128. You unroll all of them to be one column of your memory array. So like this first kernel, this 3 by 3 is 9, 9 times 128 is close to like 1000. So you have 1000 data. You unroll this into one column of your memory array. And different filter, you can unroll that into different columns. So what you need to do is later is for the input feature map, also you unroll that, and then you can load in them in parallel, and then you can do this in memory computing in this fashion. Of course, this is a very large matrix if you do this kind of unroll. For typical convolution layers, if you unroll that, it can be like 1000 by 1000 matrix size for that memory array. So it's very large. So the better way to do this is to look at the location of each element, and then you can use different subarray to do this. For example, if you have 3 by 3 kernel, and here we prefer to have a non-subarray to do this. So eventually each subarray is doing just one kernel, one element across this channel. So for example, this one is going to, we are going to only store 128 here to this subarray, and then this 128 element is going to store in another subarray, and you have none of this 128 column. So that means you have none arrays to store this. If you do this, then you can better reuse your input feature map, and then you can save the intermediate data transfer. So I'm not going to go to the details, but I just want to say that there are many strategies you can explore to better utilize your memory to store these weights in the kernels. And in our group, we developed some benchmark tool to estimate the performance of the hardware accelerators using different technologies. And we call it neural scene. And there are many choices. It's like the NV scene you are using for the memory benchmark in your last homework. But this one is to extend the scope to this in-memory computing and machine learning accelerator. We are going to model the whole accelerator's performance using similar approach as NV scene, but with additional circuit modules, because you do computation, you need those additional modules for example, your accumulation, pooling, activation, and so on. So we have those available in this model. And recently we did some integration of this model with the popular machine learning package like the TensorFlow PyTorch. So you can run everything in Python environment, and then you can call the TensorFlow and PyTorch to get you the algorithm level performance, like the accuracy for your image recognition task. And then you can generate the traces from the algorithm, and then that means the weight and the input pattern, and then you load that into the neural scene and then run the circuit level performance. Given this kind of weight and inputs, then what kind of latency energy you are going to spend if you run this kind of algorithm on this particular chip. So this is the work in my group, and we have that available in the GitHub. And the first version is just for inference, and we are still working on the training version for this platform. And this is the chip architecture we modeled in the neural scene framework. So it's a hierarchical model, and at the chip level have global buffer to save your input and output feature map, and then we have tile. Within tile we have PE. Within PE we have subarray, and within subarray then we have different technology choices. As we discussed, the SRAM or this two-terminal non-volatile memory like RRAM, we have seen that, or the three-terminal devices, the ferroelectric FET, or floating gate transistor, also possible, flash. So then we can model different technology and then build up the chip architecture and then run the estimation for the performance, like the latency, area, power consumption, energy for your machine learning workloads. And here are some results. I will skip that. So here you can generate those kind of table if you run the simulation, and it will give you the energy efficiency number and the throughput. So this is what we care about as a metric to evaluate the chip design. And also it can also help with some of the reliability analysis, because your memory cell may have the retention problem. Your weight stored as a conductance of your memory cell, and then the conductance may drift over time. That means your accuracy may change over time. So then we also can enable this kind of estimation for the accuracy as a function of time. Okay, so a quick summary. We talk about this machine learning accelerator, and of course, the industry's mainstream is to develop this digital approach like a TPU. You build this MAC using multipliers and adders, digital circuits, and then you optimize the data flow. But still we see the challenge or bottleneck in those design is still the memory access, because in that design you still need to access memory somewhere from the buffer. So here the research is to embed the computation into the memory array, and we call it computing in memory or in-memory computing. And in this case we use SRAM as a demo, but we are also interested in those emerging technologies because they are potentially higher density than the SRAM. And then we show the advantages even in silicon, tape out, the chip level. We see the advantages in the energy efficiency and the throughput. However, the key challenge, as we discussed, is the inference accuracy degradation because of the process variation inherent to your analog computation. So this is a key challenge. There are some possible mitigation strategies. For example, you can calibrate each chip. That means after the fabrication, you have the process variation. Different chips may behave differently. So you need to fine-tune your neural network model to fit with each chip. So you can recover the accuracy degradation for each chip. Of course, you need to spend more effort to fine-tune the model. And this is additional cost for you, but it's possible. So those are the challenges. Of course, ADC is a challenge in this design, and we are still working on those problems in our group. So with this, I'd like to end the lecture for the whole semester, actually. And we are done with all the lectures. I will